Hello, everyone, and thank you for joining us on today's Sensafili Sparring Partners webinar. Does 5G deliver the user experience it promised? Monica Paolini, principal at Sensafili, will discuss this topic with two guests today. Monisha Ghosh, research professor at the University of Chicago and incoming professor at the Wireless Institute at the University of Notre Dame, and Bertrand Hochwald, Freiman Professor of Electrical Engineering and co-director at the Wireless Institute at the University of Notre Dame. I'm Kendra Chamberlain, and I will be our moderator today. Sparring Partners webinars, we watch our debaters discuss a topic on video. We would like to encourage our participants to participate in the conversation today. Please share your comments and questions using the Q&A button at the bottom of the Zoom screen. All comments are visible to all participants, so please keep the conversation polite and respectful. Our speakers will do their best to address the topics as they go along and become relevant to the topics being discussed. So please do not hold your questions until the end. And finally, we will be live tweeting today's webinar. You can follow along or participate in the conversation on Twitter using the hashtag Sparring Partners. And with that, I'll hand it over to Monica.
Kendra, thanks a lot for the introduction. It's a pleasure to be here. And today we have a lot to cover. And this is a Sparring Partners that I'm really keen on having because when you look at a network, there's a lot of data of what the networks can do, peak performance, what's the best capabilities. But then when you talk to people, and probably your experience as well, you don't always have that kind of experience. And so there seems to be a little bit of a discrepancy between what the network can do and what we actually are seeing. And so today we're trying to come to talk about what is that the users are seeing, and why it is so, what's different for different technology, what kind of coverage you have. And, this is all, that's the way it is. You buy a car, but you don't always go at maximum speed. You don't want to, as a matter of fact, you don't need to. But there is a question of what are the limitations? What is that we can do better? And why do we need this data? And what we're going to talk about is, do we have the data that we need or that we should have? And how is that going to impact spectrum policy, policy in general, and the future development of standards? So there is a lot here to cover. And I have Monisha and Bertrand are excellent resources because they're doing firsthand research on all this. And they're doing it independently from universities, so university labs. So it's particularly important what they're doing because it's uncoupled from any vendor. So said that, Bert and Monisha, welcome to the Sparring Partners. It's a pleasure to have you here.
Thank you.
So let's get started. I would like you to introduce yourselves and tell us who you are, what is it you do specifically on this, and then we'll go on and start the discussion. So Monisha, do you want to go first?
Sure. Thanks, Monica, for inviting me to come on this Sparring Partners episode. I'm really looking forward to sharing some of the work that we've been doing in this area. I am currently a research professor at the University of Chicago, but I am going to be heading over in January to join Bertrand Hochwald and others at the Wireless Institute at the University of Notre Dame. Before I came to academia in 2015, I was in industry for many years, working on primarily Wi-Fi, but other wireless technologies as well. And since I came to the University of Chicago, I've also had 2 leaves of absences. One is at the National Science Foundation, where I spend a bit of time managing a lot of the academic funding that goes into wireless research. And the second stint was as the Chief Technology Officer of the FCC, which just ended in June of this year. And I'm looking forward to sharing my research in this area further.
Bert, how about you?
Sure. Hello, actually quite similar to Monisha. I spent a number of years in industry. I worked at Bell Labs for a few years, or actually several years, and then at a startup company out in California for a number of years before coming here in 2011 to University of Notre Dame. So I have a mixed background at this point, partly industry, partly academia. I saw firsthand a lot of the work that was needed to get these wireless systems, both cellular, Wi-Fi, Bluetooth, since part of the work I did was design chipsets for these types of standards and products. And so I bring some of that knowledge to academia. And now I'm working on things that are somewhat related, but at least partly having to do with issues around spectrum and spectrum policy, but also measurement of spectrum and measurement of data needed to inform policy. And so a lot of my work is focused on wireless, but in perhaps a little bit of a more broad view than I had when I was in industry.
Yes, and I think that measurement is not just for PR. A lot of the times, we just have we have the best network, we have this, we have that, but there is more than that. It is important to know what is the performance, because then we can act and improve spectrum utilization, and we'll go over that. So let's get started with Monisha, in terms of why is it important to capture, what you're trying to do is to get the user experience more than the sort of what are the specs, what is that a network could possibly accomplish. Can you tell us why is it important? And I would say that a lot of the operators clearly are capturing and analyzing all that data internally. So this is not anything, this is being done. The problem is that information stays within the operators for obvious reasons, because they need to optimize their network. But we also need it in a public, open way, because then we can have a discussion on what to do next. So maybe you can tell us a little bit about where it is that you're coming from and what is that you're doing in this area.
Sure, thanks, Monica. I think you bring up what is most important about our understanding of how wireless networks are performing. And in the time that I spent in government at the FCC, it was clear that we need more information on how these networks are behaving on the ground. So there's been a lot of press lately about how poor FCC's broadband maps are. And these broadband maps are important because a lot of policy decisions are made based on where broadband is available and is not. So if we don't have accurate maps to start with, all of the things that follow from those maps are not optimized. And so in order to really understand, I mean, you mentioned user performance and network performance, they go hand in hand. And the bottom line is, in order to really understand this performance, we really need to have good measurements of the RF environment that our devices are operating in. And there are, in my mind, two ways that one can figure out what is happening in the RF spectrum around us. One is, we build dedicated sensors, and Bert will talk about that approach. Or we use the sensor that everyone is walking around with, right? We have our smartphones, which have a number of radio interfaces on them. And so a couple of years ago, I started asking myself, what information can we get from the phones that we have? Now, each of these methods, the dedicated sensor approach, as well as the smartphone approach, has pros and cons. But I would like to point out that they're complementary. And in fact, both approaches were used in a recent broadband mapping pilot that the FCC conducted with the Postal Service early this year. And I will put some of these links in the chat. So around 2 years ago, one of my students, Mohammed Rahman, he wrote an Android app. We called it SICAP. And what this app does is basically constantly scan the APIs on the phone. It works only on Android. And we use mostly Google Pixel 5s, which came out last year. and it had 5G on it. So it's scanning these APIs every 10 seconds. It extracts all of the RF signal parameters that are available from all of the radio interfaces. And we're doing this passively without root access. So you don't need to use your data plan to do this scanning. You do need an active SIM for the network that you're measuring. So we have 3 phones, one for each of the major networks with unlimited data SIMs on them. We download the data that we capture on the phone, as JSON files, and we extract into CSVs, and then we've been analyzing the measurements. We've published a number of papers, and I'll put those in the chat as well. But what is it that we're capturing? So for cellular, we are capturing the physical cell ID or the PCI of all the cells that are visible. So many times there are apps that will only tell you the primary cell that you're associated with, but that is not the only one that is of importance. We need to know all the secondary channels. We need to know all the neighboring cells that are transmitting that you're receiving. And the APIs actually capture this, any signal at above, I think, minus 140 dBm. And this information is extracted right from the modem chip. So the values we get are the values that the phone and the network are using to optimize performance, right? So performance like measurements like RSRP, RSRQ, frequency. We get a little bit of bandwidth information, but not enough from this APIs. We can also capture LAA, CBRS, and most recently 5G in all bands, low, mid, and high. In fact, the reason we started doing this approach of measurements was to understand how LAA was going to affect Wi-Fi performance. And so once we had this app, simple walk around town, and we could immediately figure out where LAA was deployed or where CBRS is being deployed. For Wi-Fi too, we collect the RSSI, we collect the frequency, tells us the version, the bandwidth, as well as the BSSID. So very quickly, along with the timestamp and the GPS coordinates, we have information that allows us to create very, very detailed maps of all of these technologies. And as time has gone on, we've added more. So we've recently, just in the last month, added measurements, again, from the APIs on the phone on CPU and skin temperature, because what we've identified just over the last few weeks is that your 5G mmWave performance that you get on your device seems to be a function of how hot the device is getting. So as soon as the device gets hot, the data rate drops. So a lot of these detailed understanding of how these very complicated networks that have been designed are actually operating in practice. We think it's very, very important to get this real-time information. We also use 2 other apps a lot. One is a standard speed test app, and we use the FCC speed test because it can run all the download, upload latency tests, and we can download the data and analyze it later. We also use another app called Network Signal Guru, which requires root access but provides more data, such as RB allocation and other, what MCS, number of streams. There are, I'm seeing a comment right now in the chat which talks about drive testing tools. There are a lot of drive testing tools, and we have looked at them. Most of them are very expensive. As academics, we are always trying to use the tools that we can use and get the data that we need in a manner that we can access quickly and process quickly. So that's just a bit of a background as to what we've been doing. And Kendra, if you can just bring up that the first slide that I had sent you, I'd just like to give the audience a sense of the work we've been doing with this data that we've gathered. So this is a paper that was recently accepted at ACM WinTech, and I'll put the link in the chat, where we went to an area of Chicago called Hutchinson Field. This is an area where there are a lot of big events happen. The reason we picked it was what we found. If you see those blue triangles there, those are mmWave base stations that Verizon has deployed. So this is just about a 0.1 square kilometer area, and there are 6 base stations, 6 mmWave base stations deployed in that area. Just by walking a couple of hours in an afternoon, walking around that area with 3 phones, allows us to capture not only 5G, we can capture all the 4G licensed coverage. We can capture LAA, CBRS, and we can capture the 5G. Now, many times what you will see is speed tests. And while speed tests are ultimately what the user is seeing as their performance metric, what we found is speed tests vary a lot. You can be in the same position and you can watch your speed tests, and yet the numbers will go from 2 megabits per second to 150 megabits per second. What doesn't change that much is the signal strength. And so we are kind of gravitating more towards understanding what the signal strength is in an area to really understand how that translates into coverage. There isn't a direct relationship because throughput depends on network load, depends on who else is on the network, depends on propagation. There are many, many other aspects that go into the actual speed that server delays, many other things. Monica, I can go on and on, but if you want to go on to another topic, we can stop here and then,
Yeah, why don't we get Bert to tell us what he is doing first, and then we can sort of have more of a wide discussion. And I think people want to know, what's the difference that we see between different, 4G, 5G, LAA, millimeter wave, and so on. So, because Bert, you're doing something that it's highly complementary, but also very different.
Yes, it is. When you're finished with your phone call, you don't usually get a pop-up that says, how was your call today? And, how did everything go? Or how was your web session? Even if you did have that pop up every time, people are very unlikely to answer this, unless, of course, things went very poorly and you have the energy and the frustration to answer these types of questions. So from an operator's point of view, people are, when they have subscription to any service, wireless service of any kind, their most customer-facing portion of that subscription is the operator that provides you that service. But of course, the operator buys its equipment from any number of vendors, and the phone that you are using or the device you're using, you might have bought from yet a different vendor. And so there's a lot of pieces to the whole puzzle of how well something works. Part of that, of course, is the signal itself and how strong the signal is where you are and how much interference you're seeing or lack of interference. And so at the end of the day, no matter which device or operator or any other service provider you have, if you don't have signal, then you can't get coverage and you can't get any kind of data through. So part of what we're doing at the Wireless Institute is have a broad campaign to do spectrum mapping that begins with creating these little devices, and just holding one up here, that scans 6 gigahertz of spectrum and is intended to be a mobile and relatively low cost and low power device that lots of people can carry around with them, and the ultimate goal of something that's small and cheap enough that maybe it's even an attachment or part of a phone so that everybody has them. And the idea is not any one device is going to be useful by itself, but when combined with thousands, tens of thousands, or hundreds of thousands of other devices, you're going to be able to map out activity all around you in terms of where, what's active, where, and at what time. And so, and it won't be just the carriers that you are using, it'll be things you're not. So it provides activity levels and for other types of services that are around you, or the lack of activity, with the idea that if we have a very broad spectrum map, then we can get a nice picture of what's going on in over a wide geographic area, and much the way that any of these crowdsourced type services like Waze tells us the traffic picture on roads that we intend to be on.
Yeah, so this is mobile operators publish maps of their coverage, but I guess that what you can provide is something that is more detail, but also it will cover, say for instance, for CBRS, you'll be able to cover not only the operator network, but also all the GIA use, which would now be part of the operator map once they would have, and the map of the operators is not going to be as detailed in terms of what frequency they're using where. They just tell you where there is coverage.
Right. And of
Right,
course, you know, the operators are pretty optimistic with those types of maps. They want to, you know, they want to make sure people buy the services. It's very hard, of course, at the end of the day, to see what's really active where and when. And a map is by its nature rather static. And so what you want is something more real time and more dynamic, because these things change on a regular basis.
Yeah, absolutely.
Yeah, and just to add to that, with the CBRS, again, having these tools, for example, as soon as the CBRS auction happened last year, we would pick up CBRS deployed by Verizon on our phones. And you're right, the private networks, we would need a SIM for the private network if we wanted to get it with the smartphone approach. But we can pick up the other information if any network is deploying it. And right now it's only Verizon that's really deploying CBRS. We get that information right away.
Yeah, absolutely. So Monisha, maybe we can get started to talk about the results in terms of what is that you're seeing. You mentioned LAA at the beginning, but okay, maybe we can start. Let's start with LAA, and then we can go on to 4G, 5G, and CBRS in terms of, you know, what is that you're seeing there?
Yeah, and so actually a lot of this work got started with our research that we were doing on LAA and Wi-Fi coexistence. We'd been working on that for a few years at that point. This was about 2 years ago. And we were doing the standard academic approaches of doing analysis and simulations and some small lab experiments. Once we had this app, we realized that LAA is actually being deployed pretty widely in Chicago. So we walked around downtown and we saw LAA, and this is mostly small cell deployments that are going up on poles. And then we found 2 locations. This was back in 2019, before, you know, the pandemic shut everything down. We found locations in 2 university campuses in Chicago, University of Illinois at Chicago and the Illinois Institute of Technology. And, you know, when you're walking around downtown, yes, you can take the measurements, you can create maps, and one of the publications I listed gives a description of what we found, but you really can't run experiments there. It's hard to set up in the street corner in Chicago, downtown Chicago, and try to do something more detailed. So we did start doing something more detailed at the Illinois Institute of Technology. I reached out to a colleague there, and she arranged for me to get access, my students to get access. And we set up these very detailed experiments where we would take the existing LAA, which was usually on a pole, and there was this one location where it was on a pole right outside a dorm, and these dorms always have Wi-Fi in them. And then we started, you know, running different kinds of traffic over these networks to see the performance. Now, what we did observe was that the scenario that people had in mind when they developed Wi-Fi LAA coexistence mechanisms was that LAA was going to be outdoors, Wi-Fi was going to be indoors, and there really wasn't going to be much of an interference space for these 2 systems. What we found was that in certain locations, like university campuses, where there is Wi-Fi, the actual AP is installed indoors, but the Wi-Fi experience is mostly outdoors, you know, outside cafeterias and bookstores. And in those regions, these are what are called hidden nodes in wireless networks, where the access point and the base station are hidden from each other, but the devices are not. So the devices are facing interference. If you have a phone that's sitting in the middle that is trying to connect to a Wi-Fi access point on one end, but there's an LAA that does not know the existence of the Wi-Fi and is broadcasting, it interferes with you. So we did a lot of very detailed measurements, and there were a few things that really surprised us. One was the extent to which LAA is actually being used. Whenever we would connect to LAA, it wasn't just one channel, it was 3 20 megahertz channels being aggregated along with the primary LTE channel. So that would give a carrier about 80 megahertz of spectrum, and we haven't even gone to 5G yet. right? So, and the data rates that you were getting on your 4G plus LAA was stunning. You were getting, 200, 300, 400 megabits per second if you were really close to an LAA small cell, which is really, really good for a mid-band experience, even for 5G. And so we did follow on measurements where we actually compared, okay, so what does 4G plus LAA give you compared to 5G in the mid-band? Now, I should preface my statements by saying that these are very early days for 5G. What we are seeing today is certainly going to get better and better as deployments improve. But today, there is not a huge difference in throughput performance between a fully optimized 4G system that's taking advantage of LAA or CBRS versus a 5G mid-band system, because the bandwidths are becoming very comparable now. When you go to millimeter wave, it's a very different experience there. 5G millimeter wave is clearly giving you very, very high rates. And Kendra, maybe if you can bring up the second slide that I had sent you, we can go through that picture very quickly to give you a snapshot of what we saw. Yeah, so this, again, this is in the paper that I linked to in chat. So this gives us a breakdown of coverage statistics that we saw. The first one is RB usage, that's resource block. This is a parameter we don't get from SIGCAP. We get this parameter from the network signal guru thing. What you will see here, which is very interesting, is the amount of LAA usage. So AT&T does not have CBRS. They're beginning to deploy 5G mid-band, that is FR1, but the amount of LAA usage is pretty high. T-Mobile is different. It doesn't use either LAA or CBRS. What it does have is 5G standalone, which is this purple bar. So that is the only carrier that we've seen so far in Chicago that is deploying standalone. And then it also has 5G in the mid-band, but that's not standalone. Verizon seems to have pulled together many different functionalities. So they have the 4G license, the primary carrier, they have the LAA, they have the CBRS. They have FR1, but that is in the spectrum sharing mode, the DSS mode. So that's kind of difficult to tease out separately. And they have millimeter wave. The second curve, it shows you what the throughputs are. And again, this is in the area that I showed earlier, just one small area where all these networks are very densely deployed. And clearly, all of the 4G and 5G are clustering together. And it's a little bit hard to see over here, but if you go to the paper, you will see that maybe 5G T-Mobile NSA is a little bit better than the others, but it's not a huge difference. The huge difference in throughput you get is when you go to millimeter wave, Verizon's 5G. Now, keep in mind, in the picture I showed you, this was a very, very dense deployment. This is not the experience you will see in other places where it's not deployed so densely. So the takeaway from this is that, yes, 5G millimeter wave has a lot of promise if you can deploy it in the density that, for example, we saw in this deployment. On the latency side, we're not seeing huge improvements yet, but again, as I said, these are early days. I think the latency benefits will really come in when you go to standalone. But these are the things that we want to track. Going back to what Monica said early on, the reason we are doing a lot of this work is to understand, as the discussions on 6G are already starting, as to how we take the lessons that we are learning from these deployments and put them into forward discussions. And as Monica said, the network operators are doing this. They have this data. Unfortunately, for researchers like us in academia, we cannot get that data from the network. So we kind of have taken the tack of going out, collecting our own data and coming up with some conclusions and making it available, the data as well as the results.
Yeah, and it's interesting because, for instance, for LAA, so operators usually advertise 5G in a lot of detail, but LAA is something that is kind of under the radar, and I guess that there is no reason for them to advertise it as much. It's just something that it's useful for them. They use it, but they don't need to, that's not a selling point, let's put it that way, for them too.
So, Monica, I will not pretend to, tell you what, how operators make these decisions as to, how they market their products. But in my mind, again, I'm completely neutral in this whole LAA Wi-Fi debate. LAA can give you huge benefits for a cellular operator, which is why they're deploying it. But I think in situations where they could be in conflict with Wi-Fi, our results have indicated that they should be a little bit more thought paid to how these networks are deployed. There is more work that needs to be done to make the coexistence performance better.
Yeah, absolutely. But it's also interesting that it's not trivial, like 4G versus 5G. It's not, there's still a lot of life, I guess, to 4G that you're seeing at the same time.
Yes, I think 4G, by virtue of the fact that you did not have large contiguous bandwidths allocated for 4G, I think the maximum was 20 megahertz. The operators have become, and the device manufacturers, everybody has been extremely creative in getting carrier aggregation as an intrinsic part of the 4G system. And once you start aggregating carriers across bands, across LAA and CBRS, the total aggregate bandwidth that you end up with is approaching what you can get in mid-band 5G. And so I hope that some of those technical advances that 4G made will stay, and carriers will find a way to continue doing that in 5G and the standards. Because, as we all know, spectrum in the mid-band is limited. We have to use it judiciously, and we grab pieces wherever you can. And I think a lot of the spectrum sharing concepts that Bert and I are working on are to move us in that direction.
Yes. So actually, there is a quick question, and so we can go through that. It's about distinguishing the measurements deployments for SA and NSA. And I think you can distinguish, right?
Well, we have to do some tricks to do that. So we use, and these are all the tricks I've learned from my students about how you do that. So we can take the phone and use one of these apps to force it to only look at the carrier that SAA is broadcasting on. And it's not obvious. I mean, if you just let the phone do what it is, you really cannot do that. So we went through this process of forcing the phone to be on 4G only, forcing the phone to be on 4G, 5G SA only, 5G NSA. And that is how we captured the data on all of these different modes.
Yeah. So, Bert, what about you? What is that you find out in terms of the coverage? Is any difference in terms, or anything new that you found out in terms of 4G, 5G, or other bands? What's the preliminary results that you've seen there?
So the that's hard to tease out right at the moment. I think Monisha shared a link with an FCC report where our sensors were used to were actually taped to walls of some postal trucks in a trial experiment where I believe on the order of 7 trucks were driven around a Denver area, and the idea being that they would measure broadband spectrum power, and at the same time they would have phones operating so that they could correlate what they were seeing in spectrum with what the various speed tests and other things were showing on the phones. And the whole goal being that if you can get some good proxies for the user experience that are simpler than just operating phones on a continual basis, then we'll all be much, have easy ways to just measure a few key things that directly relate to user experience, rather than the whole, ask the user him or herself. And so that's only recently been done, and the data is a little bit inconclusive on that at the moment, or it hasn't, we don't have all the results from that. But clearly, the more information that you do get about what's going on around you, the the more informed you'll be, and the better you'll be able to make that correlation.
Absolutely, and I think that, so there is clearly this is just starting what you guys are doing right now, and there is clearly a need to get better data in general for all sorts of reasons. And the reason that I thought it was most sort of new to me is the fact that this is something that it's not only to understand what's going on today, but also to inform how we're going to go in terms of deploying or developing new technologies. So let's start with the future first, and then we go back to the present, maybe. And so maybe you can talk about, why do we care about this as we think about 6G or the development of 5G? Why is it relevant?
Should I?
Either of you guys.
All right. All right.
Go ahead.
Well, certainly, the big question always in front of everyone is, should we open new bands? Should new bands be made available in licensed manner, in a shared manner, in an unlicensed manner? And these are the types of questions that become increasingly important as we go on. The lower bands, when I say lower, under 6 gigahertz or so, especially below 2 gigahertz, are considered the prime waterfront property in terms of its characteristics for propagation and building penetration, and those are obviously full, or at least people think they're full. If you look at these various NTIA type charts that show you who's got which bands, you see everything, every little sliver pretty much occupied. Of course, what a sensor might tell you is that there's wide open spaces that actually, even though the chart tells you there should be activity or anomaly, there's activity here. When I look at with a sensor, I don't see any. So does that mean that I now have the opportunity to use that myself? Is there an opportunity to either share the spectrum with others? And so one of the primary things that's really needed is an accurate spectrum map below 6 gigahertz. And that means what's actively being used, not just what's on a chart. And so the more the information we can get about things happening within bands that presumably are already spoken for or occupied, is to figure out what is really active and what isn't. Then once we have that, and we might be able to say something about, can we share any of the nominally unused portions of that? And then, of course, moving from there, we have to open up new bands and figure out how these new bands can either be taken from existing users that either don't use them as well, or share them in some manner, or go into totally greenfield areas. Of course, these very high frequencies have lots of trouble with propagation and building penetration. So the types of networks we see at these lower frequencies are not likely to be similar or the same as the ones we see at very high ones. So the primary order today in developing these new technologies is what spectrum will it occupy at the end of the day?
Yeah, and if you want to
just to add to what Bert said, I think this licensed and unlicensed, there's always this huge debate that always comes up when spectrum is made available. And at least in my mind, it is clear that as we look forward, 6G or next G technologies, cellular technologies, will be making increasing use of the unlicensed bands. So really understanding what are the best practices of how to manage coexistence in unlicensed bands is very important. And the reason is that cellular technologies were not natively designed to coexist with others in their frequency bands. So when they're faced with that, LAA came up with a set of methods, a set of ways to deal with it. But that was the first time that the cellular technologies actually moved into a band where they were not the only licensed user. I think there is still a lot of work and research that needs to be done. Standards need to be made aware of what is the user experience on the ground when these two technologies coexist. And the only way you're really going to understand that is by using these kind of methods. The other thing I want to point out is that as far as spectrum sharing goes, or even things like millimeter wave, the community, both the research and industry and even government, NTIA and others, have done a lot of work on channel measurements and propagation modeling. But oftentimes these are one-off measurements. So you go out one day and you set up a millimeter wave transmitter receiver, they're pointing at each other and you get a channel model. What we've seen is the channel model when the millimeter wave base station is mounted on a pole and there are trees in the middle and cars are going by and people have turned their backs to the base station, it's a very different thing. So being able to capture the signal information in real time in a variety of environments easily using either dedicated sensors like Bert is doing or using your phones like I'm doing, we need this information to really understand how we can share better going forward, or how new spectrum will behave from the user perspective, not just in the terms of designing the network.
Absolutely, and this is really very important. So you are you've been doing the work on LAA, which is really interesting. But what is that going to tell us about, for instance, 5G NRU? For instance, in the 6 gigahertz band, and from talking to people, you get a sense that that's clearly not the first priority for operators, which makes sense. They're just going to deploy licensed spectrum first. But does this mean that we're going to see more LAA type of deployments with NRU, even though right now there isn't any yet, because I guess we're so early on 5G? You think that that's a good model moving forward?
Well, again, this is my opinion, but I absolutely feel that 5G NRU will and should be deployed in the 6 gigahertz unlicensed band, because the amount of bandwidths you have available is amazing. It's much, much larger than what you're going to be able to get in this mid-band region if you go licensed, right? 5G NRU is also going to be standalone. So that means right now LAA is still a tethered system. It's only downlink. The uplink transmissions still going over unlicensed. 5G NRU has been designed to be standalone. And so suddenly you have, and for the user, it's great too, because as long as coexistence can be worked out well within these two different technologies, the amount of bandwidth you have, 1.2 gigahertz of bandwidth in a prime region of the spectrum, is enormous opportunity for everyone. And I do hope the carriers actually will take advantage of that, with the caveat that they do pay attention to coexistence, because it will be important. And when I was at FCC and the debate on whether some of the spectrum should be licensed versus unlicensed came up, one of the factors that came up is that once you license spectrum, say to a carrier, that's it. At least in our current licensing regime, nobody else can use it. So an AT&T spectrum is an AT&T spectrum unless they figure out ways to lease with others. The unlicensed spectrum makes it a lot more flexible. It is much, and it creates a lot more innovation for people to be able to come up with systems that coexist better and that can use this entire wideband spectrum better. The automatic frequency control, I think, process for the 6 gigahertz outdoors is starting. FCC probably today, I think, in their meeting, they're going to be talking about it. So I fully expect to see that that approach will get way more traction, probably even more than LAA in 5 gigahertz.
But so in terms of the coexistence, who is going to be okay? So coexistence is like you need to make sure you have good coexistence, but you also need to have the right standards or regulation. So at which level, what is the most effective way to ensure good coexistence?
So at least in the US, the regulators take a very light touch to matters such as these. It is an unlicensed band by definition. And so the thought has always been that we are not going to regulate, the regulator is not going to tell you how to coexist. You industry, go figure this out. And again, my personal opinion here, I think the two bodies, the 3GPP and the 802.11 or the Wi-Fi group, they do liaise on this, on coexistence. I think they could be doing a better job in recognizing what are the fundamental issues. The other coexistence, which has not been addressed much, and we did see it in our measurements, is coexistence between LAA. So an AT&T LAA being deployed right next to a Verizon LAA. So in Wi-Fi, they have these mechanisms for dealing with hidden nodes that are very native to the way the Wi-Fi protocol works. LAA doesn't have a lot of those native hidden node detection protocols. They just rely on sensing mostly. And that works in many cases, and it doesn't work in many cases. So as operators are thinking about deploying 5G NRU and 6 gigahertz or more dense deployments of LAA in 5, that is going to become an issue too. It's because now you have not just one Wi-Fi and one LAA, but you have many Wi-Fis and many LAAs. And that's a very good research problem actually for academics to look at. And there's a lot of innovation that can be done there. But the standards, I think, need to work a little bit closer together.
Yeah, and I think that in this case, you cannot just expect the 3GPP or the Wi-Fi Alliance to do it on their own. You need to have somebody coming together, whether it's the FCC regulator or somebody, but you need to get them together. You can't necessarily just hope for people to just be well behaved.
Well, I also think that it's not, I mean, I don't speak for any operator in particular, but I've heard it said in one form or another that licensed spectrum or monopolistic type of spectrum is key for an operator to want to roll out any kind of a network, because they don't want to spend the billions of dollars in rolling out a network in a band where others can presumably intrude or ruin the so-called customer experience for them. So there, I think part of what operators are likely to say or position is that licensed spectrum has to be the backbone for the network. And there are other, what you can opportunistically do things like LAA or maybe 6 gigahertz types things when they're around, but it's not clear to me that there's the incentive to roll out things in those areas exists in these shared environments where others can presumably also intrude on you.
Yeah.
So yes, I think the unlicensed deployments are going to be an urban thing. I don't think you're going to be able to, you're not going to have LAA deployed on cellular towers along highways. So you definitely need the cellular licensed backbone for this wide footprint that cellular carriers need to continue having, right? It is when you get into these small dense pockets like a stadium or a university or an airport where you need a very, very dense coverage and your licensed spectrum isn't enough to serve all the consumers' needs, it is going to definitely help you in those kind of deployments, which is the way the carriers are rolling out. Absolutely.
Quick question from the audience from Osgur, and it's asking, why is LAA not more popular than it currently is? It's been in 3GPP specs for a while, but only limited countries implemented it. Same with carriers. I was actually surprised, and to hear from operators too, that there is actually more than it's being advertised. So I don't know about other countries, but in the US, actually, there seems to be quite a decent amount.
Yes, and that was actually our first surprise when we did our first measurements in downtown Chicago. It's like there's LAA everywhere, right? It is being deployed. Of course, you need newer devices to be accessing it. So your older phones are not going to be able to access LAA network. So we needed the Google Pixel 5, maybe even the Google Pixel 3s and 4s can connect to it. But if you have an older smartphone, it is not going to connect. We did notice also, which is actually good, that we needed to be doing a pretty big download for the LAA to be activated. So it's deployed, but it's not necessarily kicking in for everything you're doing. It's only if you're trying to download a huge file that the network will now use the LAA part of the spectrum to push that to you. So for example, one of the things we noticed is that real-time streaming traffic never went on LAA, because that is, as Bert mentioned, you cannot guarantee QoS on unlicensed shared band. So anything, and this again brings up the topic of what applications go over what spectrum. So if you're trying to do something which has tight guarantees on latency and QoS, you would not necessarily put that on an unlicensed shared spectrum. If you're just doing a file download where it doesn't matter where speed, where the pipe you have matters, push it to LAA.
Yeah, but everybody benefits from it anyway, because
Yes.
even if only a few people that have a lot, that use a lot of traffic, use LAA, that means that there's more capacity for people with older phones that do not have LAA. So
Exactly.
it's good for everybody, even though few phones can use it. And I wanted to talk about that, but before, I want to make sure, because we're kind of running out of time, and so I want to talk about the spectrum sharing that I know that Bert cares a lot about, and that there's a lot of the reason for doing to look at the coverage across all the bands. And this is I guess that this is the strength of doing it from university research or independent viewpoint, is that you can look again at how the sort of the holistic, how is spectrum used, because being able to use spectrum more efficiently is absolutely crucial. It's not just who owns the spectrum, it's how it's being used. And this is why, you can comment on the importance of doing it in real time. And this is something that maybe you can relate to the experience we have with CBRS and 6 gigahertz. And so why do we care about doing it in real time?
Well,
And why is it important for the sharing part, for the spectrum sharing opportunities here?
Yeah, I think by their nature, if you do carrier sense or any kind of detection of energy, or any sorts of efforts on a node by node basis, their information will be limited. It may be real time, like I can detect the presence or absence of a carrier or a protocol or some sort of energy, but it's limited to where I happen to be, and with whatever radio I'm using, whatever antenna I'm using. And it's not necessarily indicative of what's immediately to my left or my right in terms of what energy is happening or activity is happening. So any one type of measurement by itself is not that useful. And so if you try to do some sort of a spectrum sharing activity that's based purely on my what I'm seeing right now, that doesn't mean that when I transmit, I won't be interfering with somebody very close to me who just happens not to be transmitting at that moment, but is receiving something from someone a little bit further away. So by their nature, these one-off type measurements, which may be augmented by location-based database types of approaches, which say it's okay to share, to use a sliver of spectrum here at a given place at a given time. These seem to be the types of mechanisms for sharing that exist today. You either make a measurement where you are, or you access a database. These are very limited in terms of their capability of doing anything real time, because as I mentioned, they're either, the database itself can't be updated very quickly, and the local measurement by itself is very incomplete. So having a map that is constantly evolving with time in some real-time manner is key, really, to getting efficient use of filling the holes in the spectrum that are currently not being used. And that can only be done in some crowdsourced way, really. And that's the target of what we're trying to do.
Yeah, because, okay, so let's look, for instance, at a 6 gigahertz, where there's basically, it's a database type of approach. Because, I mean, I guess the rationale there is like everything is fixed. So if you have a fixed link, you have a fixed link.
Right.
You should have it, so is that working well enough? Do we really know what's going on in 6 gigahertz? Or do we know enough to actually take the best advantage for 6 gigahertz outdoors?
Yeah, I think it's very early days right now. The AFC is just rolling out. But one thing, as Bert alluded to keep in mind, is pretty much all of these database approaches to spectrum sharing rely on propagation models. So we know these are fixed links, as you said, we know the antenna patterns, we know the heights, we know where they're pointed to each other. And then we throw propagation modeling on top of that to figure out what the interference radius is going to be. And then we keep devices out of that interference region, right? Now, the problem is that these propagation models can often be very, very pessimistic, pessimistic from the point of view of sharing. And so augmenting these propagation models with what you're actually measuring on the ground is, I think, very, very important, because there is so much that goes into it. RF propagation is part science, part art. Yes, if we knew exactly every reflection of every obstruction that was happening, we would be able to predict what was going to be the RF signal strength at any location. But to be really able to maximize the utilization of shared spectrum, we have to find a way that we can continually update these databases. So even if you use databases, can we find a way to continually update the propagation information that they're seeing? And some of these methods will allow us to do that, both the sensor-based methods. So right now, actually, we got a Samsung S21, which has a 6 gigahertz interface on it. And we're starting to take measurements in that band already. So, but I think that the methodology or the notion that this needs to happen is very important.
Yeah, absolutely. And so we need to have, I guess it's a different approach, because these propagation models were designed to deploy a network, or to, right. It's a very different mindset. When you look at it from the sharing perspective, it's a very different. We just need to have a different tool to deal with that.
Well, right. Propagation models, like you say, are often used as a starting point for a deployment. These various tools that are use these models, but drive testing at the end of the day tells you whether or not any of these models are any good. So only over long stretches of time do they ultimately get validated or invalidated by extensive amounts of use of the network.
Yeah, and it's also, I guess, useful to understand what is that the incumbents are doing with the spectrum actually, and to give them also the comfort that sharing is not going to have a negative impact on what they're doing. Because I guess that's sort of like the attending issue is that, okay, you say that we don't use the spectrum, but if somebody else uses the spectrum, is that going to create a problem for us? Right, so that's, which is a way to support spectrum sharing.
Yeah, and I think the more, I just wanted to tie in a lot of what's also happening in the research community and in industry is the use of machine learning and AI to bring that to wireless. Wireless is an area that, yes, there is some network optimization that takes advantage of these tools, but a lot of what is hampering this is the lack of enough data. And part of this effort is also to build up databases that can be now used to start testing with AI and machine learning tools to extract more information. So one of the biggest things, and I think there was a comment on this, is how do you correlate throughput with RF energy that you're measuring? It's not easy. It's no linear relationship between this is my RSRP, this is my throughput, right? Because the network is such a complicated beast. There are so many overlapping cells, there's interference. But as we gather more data, we can start throwing a lot of these learning tools to it to try and predict what the throughput would be given this network deployment that we're seeing.
Yeah, and you can use, I guess, AI or a better way to optimize traffic management when you have situation of high traffic levels, so that, because right now you have a handset that gets whatever channel is available. It's pretty, basic, like whatever needs tries to get the right channel. But if you look at it on a population level, when you have all the devices there might be ways to optimize it, which right now, as I understand, is not done yet. But if you have the network and the devices collectively cooperating, you might have a better way to assign which device. So as you were saying, you know, with LAA, you use only LAA when you do some specific application or you need a lot of data. So I think that there is a lot that we can do in that area, but we need to understand what's going on and then have the optimization using AI and other things. Do you think that this is going to be relevant, important, feasible?
Absolutely. I think within the research community, there is a huge amount of interest in applying machine learning to wireless in general, network optimization, improving the user experience, taking into account application requirements for latency. NSF actually has a program specifically in machine learning for wireless information systems. So this is a growing area of research and application.
Actually, yeah, we didn't get to talk about the NSF, and which is, I think, very interesting because again, it's another independent effort. And we are at the top of the hour. Maybe you can just very quickly tell us what is that? What's that about?
Yeah, no, there's something called the Spectrum Innovation Initiative that the NSF is sponsoring, and Notre Dame is leading one of these centers. I put the link actually in the chat, and the whole idea behind one of these centers is to really discuss things around spectrum, whether it's policy or technical. And there's many universities involved, and I pointed people at the website if they're interested in learning more about that.
Yeah, so we need to go now, but maybe what we could do once that takes off, we should just reconvene and see what, you know, what is that we're finding out, because this is, I think it's really important to have all this data. So with that, thanks a lot, Monisha and Bernd, and we give it back the line to Kendra.
Thank you.
Okay, great. Thank you, everyone. That will conclude our webinar for today. Thanks to our speakers, Monisha and Bert, for that great conversation. And thank you to our audience for your questions and comments. This webinar will become available on demand and as a podcast in the coming days on the sensiphilly.com website. You can also sign up for our next Sparring Partners. That will be November 4th. On the new rule for mobile operators with Jason Inskeep at AT&T. Registration for that is also available at sensiphilly.com. Thanks again, and we look forward to seeing you at future events.